Hello all. We are going to start a new topic, that is recurrence relations. Earlier in the earlier video, I have told about how to solve recurrence relation with non-homogeneous part to be some constant. Okay. Now in this video, I am going to talk about how to solve recurrence relation where the non-homogeneous part is some exponential function of the form a beta to power n. Okay, this is the second case. Here we are talking about whenever the fn part is of the form a beta to power n, where beta is not a characteristic root. Okay, if this beta is not a characteristic root, we can do this by one example. Suppose we have to solve the recurrence relation an plus 6 an minus 1 plus 8 an minus 2 is equals to 7 into 5 to power n. Okay, again this is a linear non-homogeneous recurrence relation of order 2. Okay, where the non-homogeneous part is 7 into 5 to power n, which is an exponential function. Okay, so what we have to do, first of all, we have to find out its homogeneous solution, and for homogeneous solution we have to write its characteristic equation. Okay, here we are saying the characteristic equation for this given recurrence relation will be, that is, r square plus 6r plus 8 is equals to 0. Okay, this is obtained from here. R square plus 6r plus 8 is equals to 0. Okay, if we simplify this, you will get r plus 2 into r plus 4 equals to 0, and therefore the value of r will be minus 2 and minus 4. Here we have got two characteristic roots which are real and distinct. Therefore, the homogeneous solution will be written as an h equals to c1 minus 2 raised to power n plus c2 minus 4 raised to power n. Okay, where this c1 and c2 are constant. So this is about homogeneous solution of the given recurrence relation. Now what we have told, in this case beta is not a characteristic root. Okay, why we are doing this? So because 5, here we have 5 to power n, and this 5 is not a characteristic root. As we can see here, minus 2 and minus 4 are the characteristic root, but 5 is not a characteristic root. Okay, therefore for that condition we have to consider that the particular solution is of the form c into 5 to power n. Okay, as I have told you, whenever we are solving any non-homogeneous recurrence relation, we have to find out its homogeneous solution as well as particular solution. In order to find particular solution, we have assumed that it is of the form c into 5 to power n, where the c is any constant. Now, this is the value of an. So that's why we can put the value of an in the given recurrence relation. We can also find out the value of an minus 1 as well as an minus 2. Okay, so therefore in place of an we have written c into 5 to power n. In place of an minus 1 we have written c into 5 to power n minus 1, and in place of an minus 2 we have written c into 5 to power n minus 2, and that will be equals to 7 into 5 to power n. Now we can take 5 to power n common here, and this 5 to power n will be cancelled from both sides. Okay, so we will obtain c plus 6 by 5c plus 8 by 25c, and that will be equals to 7. Okay, now if we simplify this, you will get c equals to this 175 upon 63 in this problem. Okay, now after getting the value of c, we can place it into the given recurrence relation, a given particular solution, and this particular solution now can be written as 175 upon 63 multiplied by 5 to power n. Okay, and as you know, the general solution will be given as the sum of homogeneous solution and particular solution. Therefore it will be c1 minus 2 raised to power n plus c2 minus 4 raised to power n. This is the homogeneous solution part, plus 175 upon 63 5 to power n, and that is the particular solution part. Okay, so by this way we can solve any recurrence relation whenever the non-homogeneous part is exponential function of the form a beta to power n, where beta is not a characteristic root. Okay, now if in the given problem statement we have provided with some initial conditions, then on the basis of that initial conditions we can evaluate the value of c1 and c2, and since it is not provided, therefore we can stop here. Okay, so this is the way to solve the problems whenever the right hand side, or you can say whenever the non-homogeneous part consists of exponential function. Okay, in the same way we can talk about the third case whenever this fn part is of the form a beta to power n, where beta is a characteristic root of multiplicity m. Now whenever we are saying beta is a characteristic root of multiplicity m, it means the beta root will appear for m times. Okay, for the given recurrence relation, beta will appear as a characteristic root for m times. So that's why this is called to be as beta characteristic root of multiplicity m. Okay, now let us say we have to solve this an minus 6 an minus 1 plus 9 an minus 2 is equals to 2 into 3 to power n, with the initial condition a0 equals to 1 and a1 equals to minus 3. Okay, in this problem here, first thing we have to do is, as you know, we have to find out its homogeneous solution, and that will be obtained by writing its characteristic equation, and this will be written as r square minus 6r plus 9 is equals to 0. Okay, if we simplify this, you will get r equals to 3 and 3. Here 3 is a characteristic root of multiplicity 2, because 3 appears as two roots of this given recurrence relation. Okay, so that's why here, since 3 is a characteristic root of multiplicity 2, therefore we can write its homogeneous solution to be as an h equals to c1 3 to power n plus c2 n into 3 to power n, where c1 c2 are constant, and here we have multiplied with n because root 3 is being repeated. Okay, after writing this homogeneous solution, now next thing we have to do is we have to obtain its particular solution. Okay, so one thing we have to consider here, whenever beta is a characteristic root of multiplicity m, in that case we will assume that the particular solution is of the form c n square 3 to power n. Here we have multiplied with n square because this 3 is a root of multiplicity 2. That's why we have multiplied with n square. If 3 is a single root of this characteristic equation, in that case we must be multiply it with n, and this will be the rule. So therefore in general we can say that whenever beta is a characteristic root of multiplicity m, in that case we will assume that the particular solution is of the form c, where c is any constant, multiplied by n raised to power m multiplied by beta raised to power n, where m denote multiplicity of the characteristic root beta. Okay, so if we put this value of an in the given recurrence relation, you will get c n square 3 to power n minus 6c n minus 1 whole square 3 to power n minus 1 plus 9c n minus 2 whole square 3 to power n minus 2, and that is equals to 2 into 3 to power n. This is done due to we have obtained, or we can write the value of an minus 1 as well as an minus 2 by simply replacing n with n minus 1 and n minus 2. So the value of an is cn square 3 to power n. In the same way, the value of an minus 1 will be cn minus 1 whole square 3 to power n minus 1, and the value of an minus 2 will be cn minus 2 whole square 3 to power n minus 2. Now, if you take 3 to power n common and cancel out from both sides, you will get this one. Okay, and after simplifying you will get the value of c to be 1. Okay, and this value of c can be put in the particular solution to obtain a and p equals to c. In place of c we have written 1, so that's why it will be n square 3 to power n. And after that we can write its general solution, and that will be given as sum of homogeneous solution and particular solution. Therefore it will be this one. Okay. And since in this example we have provided with initial condition, that is a0 equals to 1 and a1 equals to -3, that's why we can evaluate this constant c1 and c2 by putting these initial conditions. Okay, so for that we have placed a0 equals to 1 and a1 equals to -3, these values in the given equation 1 to obtain the value of c1 and c2. Okay, if you put n equals to 0, you will get the value of a0. In the same way, if you put n equals to 1, you will get the value of a1 by this equation 1. So we are putting n equals to 0 and we are putting n equals to 1 to get these two equations. That is c1 equals to 1 and 3c1 plus 3c2 plus 3 equals to -3. This is obtained by putting n equals to 0 in equation 1 as well as n equals to 1 in equation 1. After simplifying, you will get c1 equals to 1 and c2 equals to -3. Now, these values of c1 and c2 can be placed into equation 1 to obtain the general solution, and that will be an equals to 3 to power n minus 3n 3 to power n plus n square 3 to power n. If you take this n square 3 to power n common, you will get the solution to be as 1 minus 3n plus n square multiplied by 3 to power n. Okay, so by this way we can solve the recurrence relation whenever the non-homogeneous part is of the form of a beta to power n, and that is exponential function. Okay, if beta is not a characteristic root, we have assumed the particular solution is of the form c into beta to power n, and if beta is a characteristic root of multiplicity m, in that case we have assumed the particular solution is of the form a into n raised to power m beta raised to power n. Okay, so these are the two things that we have considered here, and that is for case 2 and case 3 whenever the non-homogeneous part is some exponential function of the form a beta to power n. Okay, yes, I hope it will be clear to all of you. In next video I will talk about the fourth case whenever this fn part is some polynomial. Okay, thank you all.